Hello all. Today we are going to start organic chemistry, and then organic chemistry we are going to discuss today about the chemical properties of alcohol and some parts of phenol also we'll discuss today. Okay. So the chemical reactions of alcohol, right? So there are mainly. Okay, so the topic that we are going to cover today is the chemical reactions of alcohol, and then few topics also we'll discuss, that is phenol. Okay. Okay, so let us join the others students also into this session. Okay, till then, like we have already discussed about the chemical the preparation of alcohol, right? And preparation of alcohol, we have seen various method of preparation of alcohol, like the various example. Oxidation of alcohol, we know that it gives aldehyde, and further oxidation of aldehyde gives you uh, acid, right? Carboxylic acid. So basically, if oxidation of alcohol gives aldehyde, so obviously the reduction of aldehyde gives you alcohol, right? This is one of the preparation method of alcohol we have, that we have already discussed in the last session, last class. Okay, there are many other reactions that we have discussed. Hydration of alkene, that also gives you what? That also gives you alcohol. Okay, there are few reactions which gives Markovnikov and anti-Markovnikov rule. The preparation method of alcohol, basically from alkene, there are three different methods we have. First, we have already discussed. I'm giving you just a quick revision on all this. Okay, and so in 5 or 6 minutes, we are going to start with the chemical reaction of alcohol, right? So hydration of alkene we have discussed, and that gives you alcohol. Okay, and the one thing that is very important in this reaction is what this kind of reaction follows Markovnikov rule. Okay, and this reaction, ethene is the ethene is the only alkene which gives you primary alcohol. Okay, this is very much important reaction we have. That is, ethene gives you primary alcohol into this. All other alkene gives you secondary, or depending on the alkene, we also get tertiary alcohol also. So the important thing in this is what? That this reaction follows Markovnikov rule, preparation of alcohol from alkene. This is the first reaction we have here. The other reaction is oxymercuration and demercuration reaction. Okay, oxymercuration demercuration reaction. This reaction follows what kind of rule? Like we have discussed already, that oxymercuration demercuration reaction again follows Markovnikov rule. Okay, so again from alcohol, another reaction is oxymercuration and demercuration reaction follows Markovnikov. The third reaction is what? Hydroboration oxidation method. Okay, hydroboration oxidation method follows anti-Markovnikov addition of this. Okay, so three method we have discussed for the preparation of alcohol from alkene. Hydration of alkene and oxymercuration demercuration follows Markovnikov rule, and the last one is it is hydroboration oxidation reaction that follows what? That follows anti-Markovnikov addition. Okay. Similarly, hydrolysis of ester we have discussed. Okay, hydrolysis of ether we have discussed. Okay, and then reduction of carbonyl compound, carboxylic acid and alcohol. All these things we have discussed. Okay, all these things we have discussed. Okay, so basically now with the today topic, we are going to start with chemical reactions of alkene. Okay, chemical reactions of alkene. So chemical reactions of alkene. You see, so let me put the heading over here. chemical properties. Okay, and in the chemical properties mainly we have chemical reactions only, and one chemical reaction we have already discussed, I think, in the last class. Okay, that I'll give you a quick revision of that, the chemical reactions of alkene. And the reaction that we have discussed, like I have told you already, the alcohol follows mainly two types of reaction. Okay, and those reactions are what? Those reactions which follows the cleavage of OH bond. Like I'll let if I write down the structure of alcohol, we know this OH bond or ROH bond is not linear in this. Okay, this ROH bond is not linear, since this oxygen follows. Oxygen is what? Oxygen is sp3 hybridized. Okay, so it has tetrahedral geometry, and this structure is not linear. Okay, so this reaction, the alcohol which shows chemical reaction of alcohol, may takes place either the cleavage of this RO bond or the cleavage of this OH bond. So mainly chemical reactions, mainly two types of reaction alcohol shows into this. Two types. The first one that we were discussing there, that is the cleavage of OH bond. This oxygen hydrogen bond. Okay. And the second type of reaction that also we'll discuss, that is cleavage of this carbon oxygen bond into this. Okay. The first type of reaction, and in this reaction we have like discussed one reaction into this, and that reaction is what? The reaction of monocarboxylic acid, also we call it as, and we also call it esterification reaction. Okay, so in esterification reaction, what happens in this? Let's just see. First reaction, esterification. Okay, in this what happens, as I told you, that this OH bond breaks into this. Okay, so in this what happens, alcohols reacts with organic acid to form ester in this. Okay, so suppose I have taken any organic acid, that is carboxylic acid, we have R, C double bond O, and OH. Okay, and when this reacts with any alcohol, suppose H O R dash. Okay, so when this reacts with, in presence of concentrated H2SO4, concentrated H2SO4 we are using here. Okay, so what happens in this OH and H comes out as H2O, and the bond forms, the product we'll get here is RC double bond O R dash. Okay, the important thing here we have to remember is here we are getting H2O. Okay, so this bond is getting break over here. This is very important to keep you in mind. This OH bond is breaking over here. This OH and this OH and H is coming together. Okay, so this oxygen, if it is O18 we have, this oxygen is going with water molecule O18 over here. Okay, and this oxygen joins with this carbon, will get this. Okay, mechanism you can understand it very easily. H plus from this acid comes over this oxygen first. Okay, so if I write down the quick mechanism of this, R C double bond O OH plus, or if I write like this, it comes H plus from the acid, oxygen have lone pair on it. Okay, so this lone pair takes this H plus and it gives R C double bond O OH2 plus OA. Then finally what happens? This H2O comes out and we get R C double bond O positive charge here. Okay, now this positive charge, and we have what? Alcohol. So we can write down the next step, RC double bond O positive charge on it plus R dash O H. So the lone pair of this oxygen, it attacks onto this positive charge carbon atom, and finally it gives RC double bond O H R dash positive charge. And finally this H plus comes out, so minus of H plus, and we get R C double bond O R dash is the product. Okay, so this gives you what? This gives you alcohol into this. And we have discussed some few examples, two more examples into this. Intramolecular esterification takes place when gamma and delta hydroxy carboxylic acid we have. So these reactions we have already discussed, so we are not going to discuss those reactions again. Okay. Now, the second reaction which follows the cleavage of OH bond here is this. Let me write you that reaction first. Okay, the reaction with Grignard reagent. Okay, reaction with Grignard reagent also follows the cleavage of OH bond. Means reaction of Grignard reagent and uh, alcohol, right? So if I like remove this page, if I erase this completely, okay. You see the second reaction we have, which follows the cleavage of OH bond in this, and that is reaction with Grignard reagent. Reaction with Grignard reagent. You see the product in this reaction, it gives alkane as the product. Okay. You see, if I take any example, general example, if I take ROH plus R dash Mg X. Okay. As we know that this in Grignard reagent, this alkyl group has some negative charge and this part has positive charge on it. Okay. So this negative charge comes over this hydrogen of this alcohol. Okay. So this negative charge comes over here. Okay. And this goes with this oxygen here. And the product we get is what? R dash H as the alkane plus we'll get, then this Mg plus combines with this OR. So we'll get Mg OR and X we have here. This is a very common pattern of Grignard reagent reaction. Okay, so if I write down one specific reaction, suppose we have this C2H5OH plus we have CH3 MgI. Okay, so this gives this H and this CH3 combined, so we'll get what? Methane CH4 plus we get Mg OC2H5 and I over here. Okay. So the alkyl group of Grignard reagent takes the hydrogen atom of alcohol. Okay. Takes the hydrogen atom of alcohol, and that is why the reaction goes like this. Okay. So these are the reactions, excuse me, which follows the cleavage of OH bond, right? OH bond of alcohol. Okay. Now the second type of reaction we have. Okay. The second type of reaction is this. Okay, I hope you have copied all this. So you see the second type of reaction here, the reaction which involves the cleavage of carbon oxygen bond. Okay, so type 2 or second type of reaction involves the cleavage of COH bond. COH bond. Okay. One more thing that I have discussed here, that when this carbon oxygen bond has to break, okay, then how it takes place, that is one again very important thing that you have to understand. Okay, suppose we have, if I take the example over here, suppose we have 1 degree alcohol, right? So 1 degree alcohol means what? We have R, okay, CH2OH. This is 1 degree alcohol. Another one, if I take R R H OH. Another one, if I take R C R R OH. Okay, all these example, if you see this oxygen, obviously this oxygen has two lone pair on it. Two lone pair here, two lone pair here, and two lone pair here. Okay, so in which, if I ask you in which case the carbon oxygen bond is more easy to break. Okay, so the point here is what all these alkyl groups shows plus I in nature, right? Plus I, plus I, here also plus I, and here also, here also, here also it is plus I. Okay, so because of this plus I nature, because of this plus I nature, because of this plus I nature, the electron density the electron density on this oxygen atom increases, right? Because all these are pushing electron into this. Okay, the electron density on the oxygen atom increases because of the plus I nature of alkyl group. Now in which case the electron density will have maximum over here. Okay, in which case the electron density on oxygen atom is maximum. Okay, so if you see here we have one alkyl group, 2 and 3. So obviously here the electron density is maximum, and more will be the electron density on oxygen atom. It is difficult to break this OH bond, because in that case the hydrogen will be firmly attached with the oxygen atom over here, right? So this bond is difficult to break when the oxygen has more electron density on it. Okay, and this bond is easy to break. This is the one way to explain all this. Okay, now the second way is what, if the electron density is increasing, all these alkyl group is pushing electron. So obviously the electron which is coming onto this carbon atom, because of the plus I nature of these alkyl group and the lone pair on oxygen atom, obviously we have repulsion in these electron here, the electron which is coming onto this carbon because of this alkyl group, and the electron on the oxygen atom. So we have repulsion in these two electron, and because of this repulsion, this bond is weak and it is easy to break. Okay. So if I ask you the order in which the cleavage of CO bond is easier, then the order should be what? If it is, suppose if it is one, it is the first compound, it is the second compound, suppose, and this one is the third compound. The order of cleavage of CO bond is easier in tertiary alcohol because of three alkyl group, then secondary alcohol, and then primary alcohol. This is the order we have. Okay, so all those reactions in which CO bond is easier to break, or CO bond is getting break, that reaction is easy to take place in 3-degree alcohol, then 2-degree, and then 1-degree. Okay, so basically one thing to sum up all these discussion, if we have tertiary alcohol and primary alcohol, so primary alcohol goes shows reactions by the cleavage of OH bond. Okay, and tertiary alcohol shows the cleavage of carbon oxygen bond. Okay, so reactivity order is this: 3-degree, 2-degree, and 1-degree. Okay, and one more thing here, it is what, if you have allyl or benzyl. Okay, so allyl or benzyl, if this bond breaks, obviously, so we'll have carbocation over here. Okay, so that we call it as allyl or benzyl carbocation. So allyl and benzyl carbocation are resonance stabilized. Okay, so those are more reactive than this tertiary even. Okay, so here I can write down allyl. Okay, and if you have benzyl also you can write. Okay, so these things you have to keep in mind. Okay, not that much important, but yes, you can have some theoretical question onto it. Okay, now the first reaction, the chemical reaction which involves this kind of reaction. Okay, so the chemical reaction that shows this kind of reaction is the first chemical reaction we have here, that is the reaction with hydrogen halide. Reaction with HX. Okay. The reactivity order in this, HI is most reactive. HI is most reactive. Then we have HBr, sorry, HBr, HCl, and HF. Okay. This is most reactive because iodine is the best living group. That's why the order is this. Okay. Down the group, if you go, the living nature is increasing. So iodine is the best living group here. So if I see the reaction ROH plus HX. Okay. And this reaction uh, takes place in presence of anhydrous ZnCl2. Takes place in presence of anhydrous ZnCl2. Okay. And this gives you the product is Rx plus H2. Rx plus H2. Okay. The very important one, very most important point we have here that these reactions follows nucleophilic substitution reaction. Substitution reaction. Okay. You can copy it down, nucleophilic substitution reaction. If you have 1 degree alcohol, if you have 1 degree alcohol, if you have 1 degree alcohol, then that reactions takes place by SN2 mechanism. Okay, 1 degree alcohol reaction takes place by SN2 mechanism. So if I can erase all these things, I hope you have all copied this. Okay. Okay. Now 2, 3 additional point or facts for this reaction you write down. 1 degree alcohol if you have, this follows SN2 mechanism. Means there will be no rearrangement. And it is all because of the stability of carbocation. Okay, if carbocation is stable, then the reaction may follows by 2 degree mechanism or 3 degree mechanism, SN1 mechanism. Okay, SN1 mechanism. So you see here, if you have 2 degree and 3 degree alcohol, if you have 2 degree secondary and tertiary alcohol, this reaction follows by SN1 mechanism. And we know in SN1 mechanism, the reaction follows by the formation of carbocation. So carbocation formation is there, so hence rearrangement is also possible into this. Rearrangement possible. Rearrangement of carbocation, okay, possible. Okay, this point you must remember. One note you can write down here, the reaction of alcohol, reaction of 1 degree or 2 degree alcohol with HCl, okay, 1 degree and 2 degree alcohol with HCl in presence of anhydrous ZnCl2, known as Grove's method. Grove's method. Okay, so this name you remember. Reaction of HCl with 1 degree or 2 degree alcohol in presence of anhydrous ZnCl2. Okay. Now, for JE point of view, this reaction is like, if you see this reaction till now, it is very simple. Okay, this reacts and it gives you the various product that we are getting over here. Okay, alkyl halide and all. Okay, and this reaction also we have discussed in the preparation of alkyl halide also. Okay, now, as I said, that secondary tertiary alcohol follows SN1 mechanism. Even benzylic alcohol, if you also have, that also follows SN1 mechanism. Okay, benzylic alcohol. Okay, carbocation formation possible, rearrangement is also possible. This ZnCl2 is what? Anhydrous ZnCl2 is a Lewis acid. Okay, anhydrous ZnCl2, it is a Lewis acid catalyst. Okay, it has tendency to accept electron pair acid catalyst because d block Zn is like transition element, no, so it has d orbital, so it can accept electron into that. Okay, now for JE point of view, the very most important one reaction I am just going to give you, that is the effect of neighboring group in bromohydrin. Okay, effect of neighboring group in bromohydrin. Now you see, I hope you have all copied this particular thing. Now for JE or JE advanced point of view, just try to understand this fact over here on the basis of this reaction, and that is effect of effect of neighboring group on bromohydrin. Okay, effect of neighboring group on bromohydrin. What is bromohydrin? Bromohydrin are those compounds in which bromine and hydroxy group, right, present at adjacent carbon. Okay, bromine and hydroxy group are present at adjacent carbon. Okay, so if I write down one reaction here, you see this reaction carefully. Okay, so if I have CH3, CHOH, CHBr, CH3. Okay, this is bromohydrin because here we have Br and here we have OH, bromohydrin. Now, what is one very important thing that you can understand here? Okay, for this point, in bromohydrin, we have two chiral carbon. If you see, one chiral carbon is this, right? Another one is this. Bromohydrin is two chiral carbon. Okay, so it can show some like isomerism, number of isomers. Also, there are many things possible into this. But here, the next point is what? If this reacts with HBr, so H2O comes out from here. This OH and H comes out, and this Br attached onto this carbon atom, and we get here what? CH3, CH, Br, CH, Br, and CH3 plus H2O comes out into this. This is the reaction we have. Okay. Now, if I write down the projection of this molecule, okay, this molecule can have two, three structures possible. Okay, how it is two, three structures possible? Okay, you see here, if I take these two chiral carbon ones, okay, the possible structure here you see. So I'll just try to draw all the structure in one single page. You see here, this chiral carbon is here. Okay, and this chiral carbon has one CH3. Br, OH, CH3, H, and H. Okay, right. Or we can also draw this structure as this. So if I write down like this simply, okay, CH3, CH3. This side we have hydrogen, hydrogen, and here we have Br, and here we have OH. These two are same. Okay, or one possibility is what these two hydrogen are opposite side. Okay, so that also we can draw. We have hydrogen, hydrogen, Br, OH. Okay, and here we have CH3. Here we have CH3. Okay, and next possibility is what? Next possibility is again we can draw more structure from this, and that is this one. CH3, CH3, Br, H, OH. Okay. Now you see in these two structure, the identical group that is hydrogen here. You see, identical group are on the opposite side. Identical group are on the opposite side. Okay. Identical group are on the opposite sides. These two pair of structure we call it as trio isomer. Okay. Trio. This you must have done in isomerism also. And these two structure when identical group are on the same side on the chiral carbon, identical group are on the same side. This we call it as erythroisomer. Okay, these two pair of compounds are erythroisomer. Okay, when the identical group are on the same side, we call it as erythroisomer, and here we call it as trioisomer. Okay. So this is one thing. Now, in this time, very important point here it is what, because I have written this structure, these two structure for this compound only. Correct. This compound may be represented as this, or may be represented as these two. Okay. Now, when this reacts with this, which gives you this compound, the product here we have. Okay. So the possible structure here it is what? The possible structure here is what? See, and instead of this OH, and instead of this OH, we'll get what? We'll get Br here, because you see here in the product, I don't have a space here, so I am just trying to make you understand from this compound only. Okay, you see in the product here, instead of OH, we have Br. That is the only change we have here, right? So, and this reactant may have either this structure or this structure. Okay, so if the structure is this, okay, then this OH will replace by Br, and this OH will also replace by Br. Okay, so if you write down here Br, okay, so let me write down this here. Now we are talking about the structure of the product. Okay, now we are drawing this for this compound. Okay, so all these OH get replaced by what? Br. All these OH get replaced by Br. So I write down Br here, Br here, Br here, and Br. Right? This is possible. Now this compound you see, we have a mirrored image into this plane of symmetry. Okay, you see this is the plane of symmetry we have here. Okay, and this is the plane, and we are talking about the structure of product now, right? This is the plane of symmetry. It means these are what? These are meso compound. Meso compound. Okay. In this, we don't have plane of symmetry, and these two are racemic mixture of each other. Okay, you can find out the configuration. Okay, that we have discussed in isomerism. Okay, the configuration of this carbon and this carbon is exactly opposite. Configuration of this carbon and this carbon is exactly opposite. So this gives you racemic mixture. So now to sum up all these discussion, what we can say, whenever we have a reaction of HX, okay, and if bromohydrin is present, okay, then the structure of reactant molecule can be erythro or trio in the form of erythro or trio isomer. If it is erythro, then the compound will be a meso compound, which is optically inactive. And if it is trio isomer, then the compound will be racemic mixture. Okay, we can have this and this also, which on a whole, overall, this mixture is also optically inactive. Okay, but this particular compound individually and this particular compound individually is what? Optically active. Okay, so racemic mixture is what? Racemic mixture is also optically inactive, and meso compound is also optically inactive. So both compounds are optically inactive. This one and this one. Okay. So on this, on basis of on these all these facts that we have discussed on this reaction, okay, they can frame any questions. So all these points you have to keep in mind. Okay. So you can copy down these reactions. Okay. Now going forward into this, the reaction of alcohol and phosphorus halide. Okay, so I'll just remove this off. Next reaction, the reaction of alcohol and phosphorus halides. See, if you can recall, we have discussed all this reaction in alkyl halide also, because these are the preparation method of alkyl halide. Okay. So now in this reaction, the product is what? The product will be an alkyl halide. Okay. Forms alkyl halide. Okay. Reaction, you see how the reaction takes place. If you have ROH plus PBr3, this gives you RBr plus HOPBr2. This is the product we get here. HO plus PBr2. Okay. Mechanism, if you want to see, we have two-step mechanism in this. The mechanism is not that important, but just we'll discuss. ROH. Okay. Lone pair on this oxygen plus PBr3. Phosphorus has 3d orbital, so it can take this electron lone pair, and at the same time this Br minus comes up. Okay, so what happens in this? We get P Br Br O R H positive charge on it plus Br minus plus Br minus. Okay, now in this what happens? Second reaction, this Br minus attack onto this alkyl group, okay, and this pair of electron comes over here. So we'll get what? This Br minus, second step reaction, plus Br2 P OR positive charge. Sorry, I have written like this, but anyways, we'll manage. This Br minus attacks onto this alkyl group, and this bond pair of electron is taken up by the oxygen atom. So what happened? We'll get RBr first, and then we'll get HO P Br. This is what the reaction we have here. One important reaction here we have, if you have 3 moles of alcohol plus PBr3, 3 moles of alcohol plus PBr3. The reaction, if you are doing this reaction, okay. So, like you see here, 1 Br is going out. Okay, 3 moles of this we have. 1 moles, 1 Br out. So 3 moles, all the 3 Br ion goes out into this. Okay, and the product we get here again we'll get 3 moles of RBr plus H3 PO3. H3 PO. You can see the reaction is balanced. We'll get 3 moles of RBr. Okay, so like this, the reaction takes place of alcohol and phosphorus halides. Okay, so these kind of reactions we have. Now the next reaction, here we have is reaction with ammonia. Next one. Reaction with ammonia. Okay, so if you have ROH plus NH3, okay, and in this we heat this reaction in presence of Al2O3 around 350 360 degrees Celsius. Okay, alumina Al2O3 we are using, and we know this nitrogen, hydrogen, and NH3 NH bonds are polar. This H and this OH forms H2O, comes out, and it forms RNH2 plus H2. Since all the nitrogen hydrogen bonds are polar, again if you react with ROH, Al2O3, same temperature. So again one more H2O molecules comes out and we'll get R2 NH plus H2O. Okay. Now one more step if you go forward, ROH Al2O3 will get R3N plus H2. Okay. Now in this you see we are getting here, this one is 1 degree amine, it is 2 degree amine, and this is 3 degree amine. Okay, so this is the preparation method of amine here. Okay, 1 degree, 2 degree, 3 degree amine that we already have seen in the amines chapter. Okay, now the next reaction we have, and these reactions are some miscellaneous reaction we are doing here into this. The first reaction here we have, that is oxidation reaction. Oxidation reaction. Okay. Now, oxidation reaction, we know alcohol under oxidation gives you what? Aldehyde first and then acid if you further oxidize this. Okay. There are various oxidizing reagent we have. So, general thing if you write here, alcohol under oxidation gives you aldehyde, and if you do not stop the reaction till here, finally aldehyde converts into carboxylic acid. Okay. So basically, you have to memorize certain reagent into this, and we have already discussed those reagents. Okay. First reagent, suppose we have chromic acid. Chromic acid, H2CrO4. It converts alcohol into carboxylic acid. For this reagent, it is very difficult to control the reaction till here. It finally converts into carboxylic acid. Number of carbon atom will be same in all this. Okay, number of carbon atom will be same. Okay, okay, and alcohol we are using here is what? 1 degree alcohol. 1 degree alcohol gives you aldehyde and then acid. 1 degree alcohol. Okay, 2 degree alcohol gives you ketone. Okay, 2 degree alcohol gives you ketone in general. Okay, so I forgot to write down this thing here. Just you write down here. If you have 2 degree alcohol under oxidation, gives ketone. Okay, so the first reagent that we have seen is chromic acid. Okay, we can also use various reagent, right? Like we have PCC, PDC, it is D. PDC, PCC, PDC, and DMSO. PDC, DMSO. Okay, all these gives you aldehyde, or I write down like this. 1 degree alcohol gives aldehyde for these reagents, and 2 degree alcohol gives ketone. Okay, 1 degree alcohol gives aldehyde, 2 degree alcohol gives ketone into this. PCC is pyridinum chlorochromate. Okay, I'll just write down the name here. PCC is pyridinum chlorochromate. PDC is pyridinum dichromate. And DMSO is dimethyl sulfoxide. All these reagents we have come across already in aldehyde ketone chapter. Okay, one more reagent we have, that is Jones reagent. Okay, Jones reagent also oxidizes 1 degree alcohol to aldehyde and 2-degree alcohol to ketone. Okay. One very important point of Jones reagent is what? It does not affect any unsaturation. Unsaturation means any double bond or triple bond, it won't affect. Okay. These are the few reagents you have to keep in mind. Okay. For oxidation of all these things. Okay. Like suppose if I write down some reaction over here. Okay, you copied on this. What is Jones reagent? It is CrO3 in acetone. CrO3 in acetone. Aqueous CrO3 in acetone. Okay. Few reaction you see. Some other reagent also, just write down. You can use KMNO4 in H plus or OH minus, any medium we can use this. We can also use K2Cr2O7 with H2SO4, dilute HNO3 also we can use. Okay, so some reactions you write down example here. Suppose if I take CH3, CH2OH, primary alcohol under oxidation, it gives aldehyde first, that is CH3CHO. Number of carbon atom must be same, and further this oxidizes to give CH3COOH. Again, you see the number of carbon atom in all the compounds are same. If you take 2-degree alcohol and suppose to CHOH, CH3, CH3, under oxidation, it gives CH3, C double bond O, CH3, okay, ketone into this. Jones reagent, if I use, suppose if I am taking this one, H, C, triple bond, C, CH, double bond, CH, CH2OH, okay, and we are using here Jones reagent. This unsaturation won't have any effect, okay, and this CH2OH 1-degree alcohol converts into aldehyde. This won't gives us acid, okay, CH, 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 CHO. This gives us aldehyde, okay. This reaction is what? It is temperature dependent reaction, okay. One important point to write down here, when this reaction takes place above 25 degrees Celsius, above room temperature basically, at above 20 or above 25 degrees Celsius, above 25 degrees Celsius, the product will be, the product is an acid, carboxylic acid. Okay, so these reactions are temperature dependent reaction. Okay, it is important. Okay. XUC, PDC, pyridinum dichromate, PDC won't affect or does not affect double and triple bond. Won't affect. Okay. So this is also one important apart from Jones reagent. PDC also have the same behavior. 1 degree alcohol gives you aldehyde, 2 degree alcohol gives you ketone. So if I write down this one, here we have OH and here we have CH2OH. Okay. When this reaction takes place in presence of PDC, okay, and the solvent we are using here is chloroform CH2Cl2 dichloromethane. Okay. When this is a 2 degree alcohol, it converts into ketone. We'll get this first, double bond O, and it is 1 degree alcohol gives you aldehyde CH. Okay. This is what the product we get here. Okay, so these are the few reactions of oxidation we have. Okay, that must have to keep in mind. Okay, now the next reaction we are going to discuss is dehydration of alcohol. Okay, this is also important reaction we have. Dehydration of alcohol. So alcohol on dehydration, the product here is alkene. Ease of dehydration, for 3 degree it is maximum, then 2 degree, and then 1 degree. Okay. Okay. Now you see the ease of dehydration is maximum for 3 degree, then 2 degree, then 1 degree. Okay. This reaction actually may take place in presence of an acid. Okay. And that we can use H2SO4 also, or we can use HNO3 also. Okay. So if we have 3 degree alcohol, since the dehydration is easier in this for 3 degree alcohol, then for this purpose we can use dilute H2SO4 also. Okay. For 3 degree alcohol, we can use dilute H2SO4 or HNO3. Okay, dilute H2SO4 or HNO3 we can use, but in this case, dilute is preferable. We can use concentrator also. We'll get the same product. But since the dehydration is easier in 2 degree, but it is true for 2 degree also, 2 degree, 3 degree for both. Dilute we can use or we can use concentrated here also. Both will give you the same product. Okay. Now this reaction follows if you have 1 degree alcohol. One more thing, if you have 1 degree alcohol, which is difficult to dehydrate, so 1 degree alcohol for compulsory will use concentrated H2SO4. Comparatively strong acid we use in case of dilute H2SO4. Okay. This reaction follows. This reaction follows Sergeff rule. Sergeff rules. Suppose the reaction is this. C2H5OH plus H2SO4 plus H2SO4, and this is concentrated H2SO4. Temperature is around 170, 160 degrees Celsius, and this gives you C2H4 plus H2SO. Alkene is the product. Okay. If you try to see the mechanism of this, okay, mechanism I'll tell you. Basic and normal, simple mechanism here. C2H5OH we can write down like this. CH3, CH2OH. H plus from the acid, and it forms what? CH3, CH2, OH2 plus OH2 plus. So we get what? This H2O comes out, CH3, CH2 positive plus H2 plus H2. Okay. Now finally what happens? One of this hydrogen from here, since it is electron deficient, okay. So if I can write down like this, this bond is like this, and we have three hydrogen atoms, H and H. It is electron deficient, so this bond pair is taken up by the carbon atom, which is positively charged, and minus H plus comes out into this. So we get what? CH2 double bond CH2 plus H plus. Okay, this H plus is there, so HSO4 minus is also there in the solution. Plus this H plus gives you HSO4 minus from here, H plus from here gives you H2SO4. Like this, we get alkane into it. Okay, ZF product means what? The ZF product means what? This hydrogen. Okay, this hydrogen comes out from the carbon atom which has more number of hydrogen. This is what the meaning. However, in this reaction, there is no difference. We have only one option left from where the H plus comes out into this. Okay, but if you have any unsymmetrical alcohol, suppose if I give you the another reaction here, and suppose the reaction is this, and we have to write down the product into this. We have OH here, and we have CH3. Concentrated plus. Okay, so we have to write down the product into this. Remember, this is what? This is tertiary alcohol. It's tertiary alcohol. You see, if I write down the mechanism of this first, OH, here we have H plus from the acid. This lone pair of oxygen comes over here, and we get what? CS3. Okay. Finally, this H2O comes out and we get what? This ring with CS3 over here and positive charge on this. Okay. Now in this, the next step is what? We have to take this H plus out. Now for this H plus to come out, we can have two, three possibilities here, right? And what is that? This H plus may come out from this two carbon atom or this carbon atom. Okay, so when H plus comes out from this or this carbon atom, the product will be same because both positions are equivalent. Okay, when this hydrogen comes out, then we have one more product. So two possible products we get into this. One product is what? One product is this. Double bond CH2. This is one product. And another product is what? This CH3. These are the two possibilities. But according to Sergev rule, what we know that hydrogen comes out from the carbon which has less number of hydrogen. Okay, so either hydrogen comes out from this carbon or this carbon, and that gives you the major product into this. Okay, the major product here it will be what? This one is the major product according to Sergev rule, and this one is the minor product. So Sergev product is that product in which the hydrogen comes out from the carbon atom which has from the adjacent carbon atom which has lesser number of carbon comparatively. Okay, so this is the major product we have, or we also call it as Sergev product. Okay, so the product is this one is minor and this one is major. One more reaction you see on this. Suppose if I give you the reaction for this one. CS3 here and OH here. Concentrated H plus. So if you see the mechanism here, and these kind of questions to understand the mechanism is important. Okay, so if you see OH here and CS3, this OH takes H plus from the acid and it forms what? OH2 plus, and here we have CS3 as it is. Now when this OH2 comes out, so we'll get carbocation minus of H2O. So we'll get what? Positive charge here. And here we have CH3. Now, in this again, what happens? This is 2-degree carbocation. Okay. And this, if the carbocation, if one hydrogen comes from here to here, then we can have 3-degree carbocation. So rearrangement takes place into this first. Rearrangement of carbocation. Okay. This 2-degree carbocation converts into CH3 positive charge here, 3-degree carbocation by 1 to hydride shift. And finally, we have the same result, and that result is what? And that result is CH2 plus CH2 plus CH3 and double bond here. Yeah. So basically, the two things you have to keep in mind. In the first example, we have this OH and CH3 present at the same carbon. This group and this group present at this carbon only, right? So we'll get the product. Which product is this only, right? These two product only we get. And in these two, if you see what is the major product, major product is again this. According to what? According to the Serger fruit, major product is this only. So you see, for both reaction, the reactant is different, but the product is same. They're getting same product because of the rearrangement of carbocation. Okay, so this also you keep in mind that in this kind of reaction, rearrangement is also possible. Whenever the possibility of forming more stable carbocation, okay, then we'll form more stable carbocation first, and then the H plus comes out according to Serger rule. Okay, so this is another example we have done. One more important point in this you write down the conjugation. If it is the better conjugation is there, better will be the dehydration. Like some questions that they ask, in which of these molecule dehydration is easier. Okay, so one fact you have to keep in mind into this, that greater conjugation, write on this note, greater conjugation leads to greater dehydration. Greater dehydration. Now on this, if I give you one or two example, suppose two molecule I'm giving you, and you have to find out in which the dehydration will be easier comparatively. So CH3CH OH CH double bond CH2 and CH3 CH OH CH2 CH3. These two products in which the dehydration is easier. The first question is this. Second question, you see, if I give you this OH, first one, second, OH, third. Okay. So in all these, if you have to judge where the in which of these products or the molecule easier will be the dehydration. So we'll see what we'll see conjugation into this. Okay. So in this one, okay, in this one, the conjugation, if you see here, I have made one mistake here. Just to make some correction into this. This double bond should not be there. Okay, so this is the single bond we have here. This two is also not. You see the molecule is this. This double bond should be here. Here we have single bond and CH3. Okay. Why I have given this? Because conjugation is not there. No, pi, lone pair, sigma, and pi. Okay, so conjugation is not there in the previous one. So in this, the conjugation is possible, but no such conjugation is there in this molecule. So obviously, if I ask you in these two, the first two molecule, which one have more easily, the dehydration is possible more easily. In which of these molecule? Obviously, the first one is more easily dehydrated than the second one. Okay, so dehydration of this is easier than this. Now coming back with the same logic in this particular example, okay, we have greater conjugation here, pi, sigma lone pair. Okay, so large conjugation is present over here from this lone pair to this pi electron. From this lone pair to still here pi electron. Here we don't have any conjugation. Okay, so more conjugation, more will be the dehydration. So order of dehydration will be this in this example. Okay, so that's one thing you have to keep in mind. Dehydration is easier. Okay, dehydration is easier when the conjugation is more. Okay, Now that the logic that we have discussed for major product, it's Sedgwick rule, okay. But since it is an organic chemistry, so we always have some exceptions and some special cases into it, okay. So like this, some special case we are going to discuss over here. That if dehydration, one note first you write down, and then we'll see example based on it, okay. So you must have to keep all these things in mind to find out the major product, okay. Notice what if dehydration produces a conjugate double bond, then it will be a major product. Okay. On dehydration, on dehydration, if conjugate double bond is forming, then this will be the this will be the major product. Major product. Okay. Now you see some examples into it. Okay. Suppose if I write down this molecule, we have um, we have a ring over here, and then CH2, CH, OH, CH, CH3, and CH. In this, you see, if the reaction takes place, the reversible reaction, okay, H plus concentrated, then the product will be what? Here we'll have the carbocation, okay. This H plus OH, which takes H plus the carbocation, will get here. Now you see, the intermediate product, possible intermediate product is this CH2, CH positive, CH, CH3, and CH3. Okay. Now you this in this particular product, now H plus has to come out, right? And H plus can come out from this carbon, right? From this carbon, right? But before that, do we have rearrangement possible in this? Yes, rearrangement is also possible, because when you rearrange this, you will get what? You will get carbocation over here or here. This is 2-degree carbocation. Okay. So when we rearrange this, we'll get 3-degree carbocation or benzyl carbocation. Okay. So 3 possibilities we have. Okay. The one possibility is what? Either we'll get this. Okay. On rearrangement, we can have this product CH positive charge, CH2, CH, CH3, and CH3. Okay. And one more product is possible on rearrangement, and that is what? CH2, CH2, C, CH3, CH3, and positive charge on this carbonate. Okay. So these two products are possible, intermediate products are possible when rearrangement is there. Okay. How it forms? When this hydrogen comes over here, we'll get positive charge here. Or when this hydrogen comes over here, we'll get positive charge here. Okay. So the point here is what? Obviously, this carbocation is 2-degree carbocation, right? This one is benzyl carbocation, and this one is 3-degree carbocation. Okay. And we know the benzyl carbocation are most stable carbocation we have in all these three. The final product that we get according to this only. Okay, final product will be this. CH. So hydrogen comes out from this carbon, right? Here we do not have any hydrogen. So no hydrogen is here, so not possible from here. This hydrogen comes out as H plus, we get double bond here. So CH double bond, CH, single bond CH, CH3, and CH. Okay. So all these, this also gives you some product, that will be minor product. This also gives you some product, minor product. Major product is this. Okay. So two logic we can put into this. When we take this as the major intermediate, according to this, we'll get this product. And in this product, you see conjugation is there, pi, sigma, pi. Because of this H removal of H plus, we are getting this as a conjugated system. That's why this is the major product. One of the reason is this also. Another reason is in this benzyl carbocation. So most stable carbocation is this. Okay, that's why the major product forms according to this product only. That is what the meaning on dehydration. If conjugate double bond is forming, then this will be the major product. So you see here, this is the conjugate double bond we have. Conjugate double bond major product. Okay, so this is also one of the fact you have to keep in mind while forming the major product into this. Okay, so these are some important reactions that we have done already for this alcohol, dehydration of alcohol. Okay, sometimes what happens, sometimes ring expansion also takes place in case of dehydration. Okay, ring expansion also will see the next last type of reaction in this dehydration. So just you write down the heading over there, and that is ring expansion during hydration. Ring expansion during hydration. Okay. So in this, what happens? There are certain strained ring, like strained ring means what? We have angle strain over there. Okay, like we have cyclopropyl, cyclobutyl. So in case of what happens, cyclopropyl and cyclobutyl, the ring expansion takes place during hydration. Okay, so in case of certain strained ring, strained means what? Angle strain will be there. Strained ring like cyclopropyl or cyclobutyl ring expansion takes place during hydration. Ring expansion takes place during hydration. Okay, sorry. During hydration, it is dehydration. So dehydration, it is during dehydration. Okay. So if we see the example, and what happens in this, because the ring is small, so there will be more angular strain, right? To reduce that angular strain, ring expansion takes place, and the three-member ring becomes four, and four becomes five to gain more stability. Because in larger member ring, we have less angular strain. Okay. So if I see one example, if I write down here, you see, if you have this product, this reactant, suppose cyclopropyl ring we have, and here we have CH2OH. Okay. Now in this, if the reaction takes place in again acidic medium H plus, so this H plus will take this H2O. So I'm writing down this directly because we have already discussed the mechanism, and we get here what? CH2 positive sign. Okay, CH2 positive sign. Now in this, what happens? Ring expansion takes place. So either this or this electron pair comes onto this carbon atom. Okay. Suppose if I, and the best way to write down the product in case of ring expansion is to number the carbon atom. Suppose it is, suppose I have given this carbon as suppose first carbon, this is suppose we have second carbon, and this is third carbon. Okay, so what happens, suppose if this carbon, third carbon bond pair comes over here, then this third and this will join. Okay, and and these two are also already connected, right? So we have a four-membered ring. Okay, we have a four-membered ring like this. Okay, and in the four-membered ring, 1, 2, 3 are connected. So simply I just write down the numbering here: 1, 2, and 3. And 3 is connected with this carbon atom. So suppose I have given this carbon. Suppose this carbon is the star marked carbon. If I give some star mark here, so this carbon is here, because we know this star marked carbon is connected with first carbon and third carbon, because this bond pair goes over here. Okay, this also may go over here. Okay, so this 3 and 1 are connected with this, and we have positive sign where we have positive sign on the star marked carbon. So here also we have some positive sign. This will be as it is. Oh, sorry. Do we have positive sign on this carbon atom? Yes. See, the point here is what you just try to understand. This is important. Okay, otherwise you will get confused here. We have a bond pair electron here, right, between one and third carbon atom, right? And 3 and this carbon is joining. Okay, so this bond pair of electron, which is there joined with 3 and first carbon, now it is joined with 3 and this star marked carbon, right? So what happens in the first carbon atom loses its electron to the star marked carbon atom. Obviously, since the first carbon atom is losing its electron, so we don't have positive charge on the star marked carbon atom, but we'll have positive charge where? But we'll have positive charge on the first carbon atom. Okay, so here we do not have carbon atom. Okay, so I'll remove this positive sign from here, and the positive sign we'll have on the first carbon atom. So we'll have carbocation here. Okay, we'll have the carbocation here. Now, in this, what happens? The final step is what? Removal of H plus. Okay, and we have only two possibilities. Either H plus comes over here or here. But if you see, both positions are equivalent. So whether you take H plus out from second carbon or star marked carbon, you get the same product, and the product will be what? Cyclobutene. This product. Okay, cyclobutene will get here. So this is the answer we have. So any strained ring, if you have cyclopropyl, cyclobutyl, butyl, then ring expansion takes place into this to reduce the angular strain and gain the stability. Okay, so this is it for the hydrolysis of this particular thing, hydrolysis of this reaction. Okay, now the another reaction we have into this, and that we call it as pinacol and pinacolone rearrangement. Okay, pinacolone rearrangement, that we'll see next. Okay, you can copy down this, then we'll move on. Okay, so this is the last reaction we are doing in this chapter, alcohol chapter. After this, we'll start with phenol. Okay, so we'll see one more thing. We have reaction is last, but we will see some test also, test of alcohol also, and then we'll start phenol. Okay, so next reaction we have pinacol and pinacolone rearrangement. You see the rearrangement of pinacol into pinacolone. That is the meaning of this. Okay, so rearrangement of pinacol. So what is pinacol? Pinacol is this. We have carbon, carbon, CH3, CH3. Here we have OH, Here we have OH, then CH3 and CH3. Okay. You remember any of these carbon atom are not chiral into this, because if you talk about this carbon, this has CH3, CH3, similar group. This carbon CH3, sorry, it is CH3, not OH. CH3, CH3, similar group, right? So when it is similar group, so it is not the chiral carbon. Okay. So this is CH3. This compound is pinacol. Okay, and when this reaction takes place, okay, it converts into pinacolone. So if I write down the product in one simple step, H plus, we are hitting this dilute H2SO4 we are using for this purpose, and the product that we get here is C double bond O, CH3, 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 and CH3. This is pinacolone. Okay, this is pinacolone. Now, if you see the mechanism of this, mechanism is also not that tough. Okay, I'll just rub this off to get the final product to write on the mechanism. Okay, so pinacol to pinacolone rearrangement. Just write down this. I'll give you some time. Okay. Now, what happens in this mechanism? This H plus takes one of this OH minus and forms H2. Okay. Then we'll get carbocation this on this carbon atom. So like this will proceed. Okay. So you see the mechanism of this reaction. Uh, Pinacol is this. Carbon, carbon, CH3, 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 OH, and OH. Okay. So if you have H plus here, this H plus is taken up by the lone pair of this oxygen. Suppose this lone pair I'm considering. This comes over here and it gives you this as the product C, CH3, CH3, OH2, positive on it, CH3, CH3, OH will be as it is. Finally, this OH2 comes out minus H2 and we get C, CH3, CH3, positive charge on this OH, CH3, and CH3 here. Now, in this, what happens? The rearrangement of methyl group takes place. Okay, and that's why we are calling it as pinacolone rearrangement. The methyl group takes this bond pair of electron and attack onto the adjacent carbon atom. Okay, and we get finally this, that is CH3, C positive charge, CH3, CH3, CH3. Here we have OH. Now, in the final step, H plus comes out from this, and this bond pair is goes over here. We'll get what? CH3, C double bond O, CCH3, CH3, and CH3. This is what we have, pinacolone. This product is pinacolone. This we call it as pinacol and pinacolone rearrangement. Okay, to copy on this. Okay. Now the last part of this chapter, alcohol, is the test of alcohol. Test of alcohol is important one. Okay, you must have done this kind of test in your school also, lab, chemistry lab. Okay, but for JE also it is important. They ask that question from this. Okay, so test of alcohol. So like how do we distinguish primary, secondary, and tertiary alcohol? To distinguish primary, secondary, and tertiary alcohol, we have test of alcohol, and these all are experimental thing. Okay, so you have to memorize this. Okay, so first test you see, and that we call it as Lucas test. Lucas test. Okay, for this we use anhydrous ZnCl2 Lucas reagent. It is okay. So you must remember, sometimes in medical exam also they ask this question: what is Lucas reagent? Okay, so anhydrous ZnCl2 plus HCl, concentrated HCl. Okay, this is Lucas reagent. Okay, anhydrous NaCl2 with concentrated HCl. Okay, the rate of reaction in this, and that is we have done this also previous one when HS reaction we are calling it as. Okay, rate of reaction, if you see, for 3 degree it is maximum, then 2 degree, and then 1 degree. But rate of reaction is not important as far as the test is concerned. Okay. So what happens in this when the reaction takes place? Let me write down the reaction first. We have ROH, okay, plus HCl, concentrated HCl. And this we have ZnCl2, anhydrous ZnCl2. Okay, this anhydrous and concentrated I am not writing down here because I have written already here. Okay, so this gives you what? We have done this reaction, gives you RCl plus H2O. RCl plus, we always get alkyl chloride into this, okay, not halide, because we are using HCl over here. Okay, now the important point here is what? This alcohol OH is water soluble, okay, because of hydrogen bonding. We have discussed this, is water soluble. Okay, alkyl halide is what? It's water insoluble. It is not soluble in water, and since it is not soluble, so a white turbidity appears. Okay, cloudiness also we call it as, or white turbidity we also call it as. Okay, it is not soluble, so white turbidity or cloudiness. White turbidity appears. Now, depending on the time, since the rate of reaction is different for 3 degree, 2 degree, and 1 degree alcohol, if if the white turbidity appears quickly, like the time, if I tell you within 5 minutes, okay, it means if it is appearing quickly, it means it must be third order tertiary alcohol, because the rate of the reaction is maximum in tertiary case. Okay, so first case here it is what? If white turbidity appears within 5 minutes, then the alcohol is 3 degree. If the white turbidity appears after 5 minutes, then it is secondary. If no turbidity is there, then it is primary, 1 degree. Okay. So this is the reaction we have. Why 5 minutes only we are talking about? This question I think we should not ask, because it is experimental thing. Okay, we have done this kind of experiment. If so suppose when we are going to do the test of alcohol, we have done this experiment many times. Okay, so it is a repeating experiment. So whenever we take tertiary alcohol, the white turbidity appears within 5 minutes only. That's why we are taking this 5 minutes as the reference point over here. For secondary alcohol, it takes more time because the rate of the reaction is less in case of secondary alcohol in comparison to tertiary alcohol, and that's why it is more than 5 minutes. And if it is no turbidity, it means there is no reaction. It is secondary, like 1 degree alcohol. Okay, so this must you remember. Okay, one note and very important point we have as far as this JE thing is concerned. Okay, that note you write down: allyl chloride. Okay, note: allyl chloride is water soluble and no turbidity appears. Okay, if you have allyl chloride also, allyl chloride are soluble in water and hence no turbidity. So if there is no turbidity, it means either the alcohol is allylic alcohol or 1 degree alcohol. Okay, this you must remember. Okay, now the next test we have, next test you see, the second one, that is oxidation test. Okay, now in this we're using alcohol and this allowed to react with Na2Cr2O7 dichromate. Okay, sodium dichromate. It gives you product. Now, depending on the product, we can say whether the alcohol is primary, secondary, or tertiary. Okay. The first observation is what? If the product is carboxylic acid, if the product is carboxylic acid with same number of carbon atom, then the alcohol is what? It is 1 degree alcohol. 1 degree alcohol. Okay. Color change in this, orange to green. Orange to green. Okay. If the product is a ketone, if the product is ketone with same number of carbon atom, same carbon, okay, then the alcohol is secondary, like we have already done. 1 degree alcohol gives you aldehyde or acid, 2 degree alcohol gives you ketone, right? Color changes again, orange to green, orange to green. Third one you see, if no color change, then it is 3 degree alcohol. Okay, this we call it as oxidation test when there is no color change. Okay, now the next one. Okay, okay, we'll move on. The next one we have two more tests we have, and we'll finish this. The next one we have catalytic dehydrogenation. Catalytic dehydrogenation. Catalyst we use for this purpose is copper. Copper. Okay. 1 degree alcohol. Again, in this also 1 degree alcohol, aldehyde, 2 degree alcohol, ketone, and 3 degree alcohol, alkene. Okay, elimination takes place into this. So alkene forms in this one. Okay, this is just a method we have. Now the last test for alcohol, that is Victor-Meyer test. It is important. Last one. Victor-Meyer test. Fourth one. For Victor-Meyer test, see, if you have primary alcohol, primary alcohol, see the reaction in primary alcohol. We have RCH2OH, okay, and in the first step, it reacts with red phosphorus with I2 HiO. Okay, it gives you alkyl halide, okay, RCH2I, and then it allowed to react with AgNO3. When it reacts with AgNO3, AgI comes out and we'll get RCH2NO2, AgNO2 here, sorry, RCH2NO2, nitro compounds we get. Okay, now when this reacts with HNO2, nitrous acid, okay, nitrous acid, it forms nitrolic acid. Nitrolic acid is this R C double bond NOH, oxime type product it is, not exactly oxime type product is H2, H2O comes out. Okay, H2O comes out and NaOH attached into this. Okay, so this is the reaction we have. Now, when this you put into NaOH to NaOH, it gives blood red color, and this blood red color confirms the presence of primary alcohol. Blood red color confirms the presence of primary alcohol. Okay, now a similar type of reaction we have in secondary alcohol also, but there is only one change. Compound is nitrolic acid. Okay, if you have secondary alcohol, then you see how the reaction goes. Copy down this first. See the next for secondary alcohol. We have this R CHOH R. When this reacts with red P, red phosphorus I2 HI, then we'll get what? We'll get H2O comes out, we'll get alkyl halide. So RCHI and R, same pattern of reaction we have. After this, we use AgNO2. So AgI forms and we'll get nitro compound NO2 R. Now in this, if we substitute HNO2, okay, HNO2, then we get here what? H2O comes out and we'll get NO attached with it. Okay, so RCH R NO NO2. Okay, this we call it as pseudonitrile. Now, when you put this into NaOH, the last step, the color that we get is blue color. Okay, so this color you must remember. In case of primary, we are getting blood red color, and now we are getting blue color. Okay. Similarly, we have tertiary alcohol. I'll write down this only. Tertiary alcohol. And for tertiary alcohol, again the same kind of reaction we have. R COH R and R. This tertiary alcohol. In this, if you put red phosphorus I2 and HI. So again H2O comes out and we'll get R3CI. Okay, R3CI. In short, I have written AgNO2, silver nitride you're using here. And we get again Ag comes out and we get R3CNO2. Okay, now this with HNO2, since there is no hydrogen present onto this carbon atom, so this is no reaction, which further with NaOH also no reaction. Okay, when there is no reaction takes place, then it is tertiary alcohol. All these are with NaOH, it is colorless also. One more thing you write out here. NaOH gives colorless. Okay, so all these reactions are important. Color, finally, we have to keep in mind. Okay, what color we are getting in case of different types of alcohol. Okay, they ask this Victor Mayer test many times in the exams. Out of the 4 tests that we have done today, Victor Mayer test is the most important one. Okay, so this is it for this alcohol chapter. Okay, now we'll continue with phenol. Okay, so okay, so we'll start with phenol. Okay, there are few compounds of phenol. For that, you should actually know the common names. Okay, sometimes we use these names also in the questions. Okay, so you should memorize those common name of those compounds. Okay, so phenol we are going to start. Okay, now, like I said, a few compounds, common names are important. So first, if you see, if you have a benzene ring, okay, if you have a benzene ring, and on this ring, if you have two hydroxy group, OH group present at adjacent carbon, right? Like this, suppose we have double bond, double bond, double bond. Here we have OH, sorry. Here we have OH, and here we have OH. At two OH present at adjacent carbon, so we call it as catechol. Okay, CATE. CHOL. Okay, catechol. These compounds you must remember. Okay, sometimes we use the name directly. Okay, if you do not know the structure, you cannot do anything. Okay, catechol. If we have OH group present like this, OH here and here. Okay, we call it as resorcinol. 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 Okay, if you have OH group further present at this position, and this one you must have the idea of this, you must have heard the name of this, it is quinol. Okay, OH exactly opposite to each other. Okay, we call it as quinol. Okay, all these phenols, like if you talk about phenols, phenols are colorless crystalline compound. Okay, little bit property we'll discuss. Okay, these are means phenols are colorless crystalline solid. Colorless crystalline solid. Okay, since we have OH bond present here, these are capable of forming hydrogen bonding. Okay, capable of forming hydrogen bonding and hence soluble in water. Okay, soluble in water, capable of forming hydrogen bonding and hence soluble in water. Okay, if we talk about, since we have hydrogen bonding also present over here, because of hydrogen bonding also, its boiling point BP, that is boiling point, is much higher than is much higher than the corresponding hydrocarbon. Corresponding hydrocarbon means what? Like the molecular mass must be comparable. Okay, molecular mass must be comparable. Okay, hydrocarbon and haloarenes also. Okay, now the most important properties of phenol we have, that is the acidic property of phenol. Okay, so in any compounds, we know in any organic compounds, we'll solve some question onto this, because this acidic properties or acidic order, you must get question into the exam. Okay, whether it is carboxylic acid or phenol or like any other compound, right? So acidic order you must know. Some questions you must have done in GOC also, when we discuss the acidity of various compounds on the basis of various electronic effects like I effect, resonance, mesomeric, okay, hyperconjugation, anything. So based on that only, we discuss the acidity or basicity of any compounds. Okay, since we have phenol here, so phenol has acidic nature, so we are talking about the acidic property of this. Okay, so based on all those electronic effects, acidic nature, how to determine, how to establish the order in various compounds, that is very important. Okay, now coming back to this, the acidic nature of this oxide, the acidic nature is what it has. Acidic nature is nothing but the tendency to donate H plus ion. Okay, so let me put the heading first. Okay, and it is very important, you can put some logic into this and then you can understand. Okay, so we are discussing acidity. Okay, see, actually, the reactions you have to memorize. Okay, you should know like in what reaction, what product we are getting. Mechanism you can understand. Little bit of logic you can use, and you can understand the mechanism. But at the end of the day, to solve the question, you should know the what product we are getting in what reactions. Okay, this is one thing. So there is like very limited scope of understanding things. Okay, if you understand the mechanism also, then also in the exam you don't have that much time to draw the mechanism, you don't have that much space also to draw the mechanism and find out the product. So the best way to write down the answer in the organic chemistry is to memorize the um, reactions, obviously with some logic. If you put some logic, then it will be easy to memorize. But at the end of the day, you have to memorize what product you are getting under a given set of condition. Acidity is one thing that you cannot memorize because you have thousands of compounds, whether we are talking about acidity or basicity. So you cannot memorize those order. Okay, so order of this is this, this will be this. Cannot memorize it. It's not possible. Okay, so we have various electronic effects, and on the basis of that, we can understand the acidic and basic order. We can use those concepts in the exam to get the answer. Now, as we talk about the organic chemistry, in organic chemistry, we mainly defines the acidic and basic nature with respect to water molecule. Okay, so acidic. See, I'm writing down here both acidic or basic nature, but since phenol we have, so we'll discuss only acidic characteristics. Okay, okay. Acidic and basic acid and basic nature is defined with respect to H2O, water molecule in organic chemistry. We are talking about. Okay, so those compounds, like if I write compounds which increases the concentration of H plus in water in H2O are acids. Definition I'm giving you. Okay, compounds which increases concentration of H plus in water are acid, means which donates H plus ion to the water. Okay, and the compound which increases the concentration of OH minus in water H2O are base. Okay, so these are the basic definition we have of acidic and base while we are comparing the organic compounds. Right now, coming back to this phenol. Okay, phenol, the structure is what? The structure is this. We have benzene ring, right, and OH present here. First of all, we talk about the uh, nature of this group. Yeah, what kind of nature of this group we have. Okay, so since resonance is possible, so we can draw the resonating structure of this. This lone pair comes over here, pi electron goes here, and we get what? Double bond OH plus, and here we have negative. Okay, similarly, if you draw the another structure, we can draw that. I'll show you the arrow also with different color. Give me some time. We have double bond here. This double bond OH will be as it is, positive charge on the oxygen, and we have negative charge here, double bond. Again, the another structure of this will be double bond as it is, double bond here, negative charge here, double bond OH positive. One another structure of this is what we have, this ring with alternate double bond like this, and we have OH. So you see this pile in this lone pair comes over here, pi electron goes here. Again, this negative charge comes over here, and this pi electron goes here, so we'll get this. Now this negative charge comes over here, and this pi electron goes here, we'll get this. Now when this pi electron goes here, and this pi electron goes here, so we'll get this product. All these are resonating structure. Okay, and in this resonating structure, we are getting negative sign at ortho and para position. Okay, you see in the ring, if you draw the resonating structure in any benzene ring, ortho and para position are the most effective position we have. Okay, so what we are getting negative charge at ortho and para position. Para position. Now, the important thing here it is what? If you have any electrophile, just we'll discuss a bit of reaction also here, because later on we are going to see the reaction of phenol also. So if any electrophile you have, so that electrophile are like can attack easily on ortho or para position in comparison to the meta position, because ortho and para position are what? Ortho and para position are the electron rich, comparatively these are electron rich with respect to meta position. So basically when we see the mechanism of the reaction of phenol, mainly we'll get ortho and para substituted product only. Okay, one thing is this. Now another thing is what? Since this OH group increases the electron density on ortho and para position, okay, through resonance, so we call it as this group is what? The OH group or hydroxy group is what? It is ortho, comma, para directing group. Ortho para directing group. Okay, this is also we can say. Now, coming back to this acidic part of it, there's two things you must keep in mind. This helps you in understanding the reaction of phenol. Okay, we'll do this later on in this chapter. Now, coming back to this acidity of phenol, so let's see how this phenol donates H plus ion and shows acidic behavior. Okay, so if I write down this OH, and when this phenol donates H plus, so it forms what? O minus and H plus. This is nothing but the acidic nature, tendency to donate H plus ion. Okay. Now this ion we call it as phenoxide ion. Okay. This ion we call it as phenoxide ion. Okay. Now, and this is the conjugate base of this also. Okay. It is the conjugate base of phenol. How do we draw conjugate base? You must have done this in ionic equilibrium also. Conjugate base, how we can write conjugate base? Any molecule if you have, you remove H plus ion from that, the negative ion or anion which is left, that is the conjugate base of that particular compound. Suppose if I take H2O, right? The conjugate base of this will be what? Remove H plus from this. OH minus is the conjugate base of H2O. If you take NH3, what is the conjugate base of this? NH2 minus. Okay, if you take ROH, what is the conjugate base of this? Remove H plus, you'll get RO minus conjugate base. If you take H2SO4, how do we get conjugate base of this? Remove H plus from this, we'll get HSO4 minus is the conjugate base of this. Further, the conjugate base of HSO4 minus is what? SO4 2 minus. Okay, so all these are what? Conjugate base. Now, so this is the conjugate base of phenol, phenoxide ion. Okay, now if this conjugate base is stable, okay, then it means what? This reaction has tendency to go in forward direction. Okay, if it is not stable, then the reaction will not go into forward direction, means removal of H plus is not possible. Okay, the meaning of this is what? When this phenol loses H plus ion and gaining stability, it means it has tendency to lose H plus ion. If it is not gaining stability, then the tendency to lose H plus ion is less. Okay, and acidity will be less. Correct. So now any substituents present in the ring, okay, which stabilizes this phenoxide ion will increase the acidity of phenol. Okay, because the substituents at ortho and para position we are talking about, the meta position will not have any major effect. We'll say, we cannot say minor effect, we cannot say effect, major effect we are talking about. Okay, because meta position is not affected by the OH group over there. We have seen that meta there is no negative charge at meta position. Okay, so ortho and para position, if it contains any substituents which is either electron donating or electron releasing, according to that the stability of phenoxide ion will change, right? And one thing we have already discussed, that if phenoxide ion is more stable, the tendency for this reaction to go into forward direction will be more, and hence the acidity will be more. Okay, so write down this particular thing first. More stable phenoxide ion, phenoxide ion, more will be the tendency for this reaction to go in forward direction, and more will be the acidity. More will be the acidity. Correct? More stable peroxide ion, more will be the acidity. Correct. So you see here, if one group is present, suppose here, ortho position. Here we have OH. If you draw the equilibrium of this G, and you'll get O minus here plus H plus. Okay. Now you see, if this group is electron releasing, right? So it pushes electron into the ring. So in that way, the negative charge density on this oxygen is increasing and stability of phenoxide ion is decreasing, right? If this group is electron withdrawing, so you withdraw the electron, right? So its negative charge gets more stability, and hence the acidity will be more. Okay. So what we can write, electron releasing group decreases the acidity of phenol, and hence, sorry, electron releasing group decreases the stability of phenoxide ion, and hence decreases the acidity of phenol. Okay, I'll just write down this fact that you have to keep in mind. Okay, so what we can write, if G is electron releasing group, ERG, okay, then stability of phenoxide ion, decreases, and acidity, if stability of phenoxide ion is less, acidity is also less. Okay, if G is electron withdrawing group, EWG, then stability of phenoxide ion increases, and hence acidity increases. Okay, so these are the two facts we have that you have to keep in mind to understand the or the to find out the order of various um, like compounds, acidity order of various compounds. Okay, so we have to discuss what we have to discuss the um, acidity of phenol. Okay, so theory we have discussed already. Okay, now you see some questions that is based on this, and you already, I like assume that you have idea of electron withdrawing group and electron releasing group. Okay, so if I write down the first question, we'll see 4 or 5 questions onto it. Okay, because these are important, you will have a brief, revision of concept of GOCOs. Okay, so we'll see that. Suppose I write this compound, the first one. we have OH here, Cl at ortho position, okay, then Cl at meta position, then Cl at para position, and then we have simply phenol. Okay, now in this compound we have to find out the order of acidity. Okay, so you see here chlorine has lone pair of electron also on it. I'll just write down in one compound only, okay, and then write down everywhere. Okay, so and this has what? This has minus I effect, so it has tendency to withdraw electron. It has tendency to withdraw electron, tendency to withdraw electron, and here it is phenol only, right? But if you consider lone pair on this, then because of lone pair, it has tendency to resonance also, right? This lone pair comes up because we have pi sigma lone pair. Lone pair comes over here, this goes here, okay? So two effects are possible into this. Please understand this very carefully. Two effects are possible. One is minus I and other one is plus R or plus M, electron releasing. One is the electron withdrawing and other one is electron releasing, okay? So because of this, minus I will stabilize the phenoxide ion electron releasing group, stabilize the phenoxide ion, acidity increases. But plus R and plus M destabilize the phenoxide ion electron releasing group, and hence the acidity decreases. Which two factor comes into the picture that you have to understand here, and how do we judge that? Okay, now the thing is what, if you have plus R and plus M effect possible, you see this carbon has 2p orbital here. If I write down, this carbon has 2p orbital, second period element, and this chlorine has the valence shell 3p orbital. Okay, when the resonance is possible, when the size of these two orbitals is comparable, 3p is comparatively bigger in case of in comparison to 2p, right? Since we have different orbital present, different shell orbital present, this one is larger, this one is smaller, so here we don't consider plus R and plus M effect. I hope is it clear? Okay, here it is plus Rm plus M effect is not possible. If you have fluorine present here, then this plus Rn plus M will be dominant. If fluorine present over here, because fluorine has 2p orbital, carbon has 2p orbital, so both orbital are comparable, so resonance effect is possible over there. Okay, so now we consider only what? We consider only I effect into this, and that is minus I effect. And minus I effect is what? Minus I effect is electron withdrawing, and it is distance dependent also. Minus I effect is electron withdrawing, distance dependent also. More it is closer to the OH group, more will be its effect. Okay, so obviously the first one the phenoxide that forms over here is most stable because it is closer to this. The first order is this, the first one is this, second one is obviously this, third one is this, and fourth one is this, because there is no effect present over here. Okay, so order of acidity will be this, maximum and then minimum. Okay, now coming back to the next example, which is like the most important one and very good example, we are right down here only. Second one, suppose if I write down different halide group present, different halogen present, we have OH here, here we have chlorine, fluorine, then we have bromine, and the last one we have iodine. Okay, now you see here, this chlorine has what kind of effect with the logic that we have discussed just now? This chlorine has minus I only. This chlorine has plus R and minus I. Okay, bromine has minus I, and iodine has again minus I. Okay, since this one has 2p orbital, so resonance also possible into this. So because of plus R, the acidity of this decreases. Minus I will try to increase the acidity. Minus I nature of fluorine is maximum, but it shows plus R also, right? So the overall order, if you consider plus R and minus I here, the order of acidity is maximum for, and we have two effects over here. So this kind of question, when we have two effects possible, then this kind of question goes is based on what? The experimental value. Okay, if we talk about the pKa value of this, the pKa value of this compound is 3.99. Okay, this value you should not memorize. 4.14, 4.2, and this is 4.28, around 3. Okay, so pKa value is minimum for this, hence its acidity is maximum. Okay, as like if you consider chlorine, bromine, and iodine only, in all these three we have only minus I effect, and minus I effect of chlorine is maximum, so obviously this one is most acidic in these three, right? Now in case of fluorine, what happens? Its minus I effect is maximum in all four. Okay, so if you consider only minus I effect, maximum for fluorine we have, then chlorine, then bromine, then iodine. But fluorine shows plus I also, sorry, plus R also. Because of plus R, its acidity decreases a bit. Okay, and it comes lesser than chlorine than that of bromine and iodine. That's why the order is this. So in this case, we have plus R and minus I both effect possible, and the combined effect of this is what? This one. Okay. Now, the next example you see, if you have phenol and this phenol contains methyl group present. Okay, I'll just rub it off. See, we are doing this comparison of acidity in detail. Okay, so if you have phenol, OH, right, and then we have methyl group present at meta position. Just a second. Okay, so I'll just write down the question again. We have phenol, OH, and then we have methyl present at meta position, OH, and then we have methyl present at ortho position. Sorry, para position, and then we have methyl present at ortho position. Okay. So now you see in this one, if you compare the acidic order of this, the acidic order is found to be this. It is maximum for phenol, then we have CH3, and for these two it is almost equal. And for these two it is almost equal. The reason of this is what? Because here we have hyperconjugation possible. At ortho and para position, hyperconjugation possible. Because we know orthopara are the OH is what orthopara diacritic group. So hyperconjugation is not possible at meta, but it is at ortho and para position. And we know hyperconjugation depends on number of alpha hydrogen. You see the number of alpha hydrogen here and here are same 3 and 3. That's why the effect of hyperconjugation is more over here, and the property will decide on the base of hyperconjugation. Equal hyperconjugation at both positions. That's why the acidity is equal. Why this one is maximum? Because CS3 has electron releasing nature. Okay, electron releasing nature. Here also we have electron releasing nature. Okay, here also we have electron releasing nature. But hyperconjugation is dominant over here. Equal hyperconjugation, that's why the order is this. Okay. Now another uh, example you see. Another example you see. If I write down this, two more example we'll see onto this. We have OH and NO2 here. OH and NO2 here. OH, NO2 here, and then we have last phenol. Okay, now you see this NO2. NO2 has minus R effect or minus M effect, correct? Minus R or minus M, because nitrogen oxygen will have double bond here. Okay, and here we have O negative and positive. This is a structure we have. This bond can go over here and it can draw electron from this uh, bond, right? This side. That's why NO2 is what? Electron withdrawing group. Okay. The electron withdrawing group, obviously it will increase the acidity of phenol. Okay. So here the order of acidity of phenol is found to be maximum for para position. Then we have ortho position, because at ortho and para position the effect is more. Then meta position, and last we have for phenol. Why this one is less? Because of what? Because of the hydrogen bonding over here. Okay, just write down H bonding. Because of H bonding, its acidity decreases than para position. Okay, this is one example we have. Okay, one last example we'll also see. One more example we'll see. Drop this. If I write down OH and OCH3 here, OH, OH, OCH3, OH, OCH3. What is the order we have in this? OCS3 are what? OCS3 are electron releasing group, ERG. Why it is ERG? Because this oxygen has lone pair on it, so it can donate the lone pair like this, okay, into the compound. Okay, so all these are electron releasing group, and electron releasing group will decrease the acidity of phenol, that we already know, and the effect of this is maximum at ortho and para position, right? Effect of OCS3 is maximum at ortho and para position, correct? So OCS3 at ortho and para position will decrease the acidity of phenol more than OCS3 at meta position. Okay, but at meta position, what happens? At meta position, this is very important. Just try to understand this. At meta, since meta position is unaffected because of this OH group, so this will not show resonance here, but this shows what? This shows I effect, and that is minus I. Okay, because this position is not affected by resonance, only this and this two position are affected. So here we have only I effect possible. And what kind of I effect? Minus I, because oxygen is more electronegative than carbon. So this will withdraw electron. Okay. So minus I effect, OCS3 shows at meta position, but at ortho and para position, it shows what? Plus R effect. Here it is plus R or plus M. Here also it is plus R or plus M. Okay. So these two will decrease the acidity and this will increase the acidity. So obviously acidity of meta position, this OCS3 phenol is maximum here because of minus I, and these two is decreasing acidity. Then second we'll have OH, and the tendency to decrease this um, acidity of ortho position is less than to that of para position. Okay, so at orthomethoxyphenol that you have, its plus I effect, its plus I effect, sorry, its minus I effect increases because it is closer to this than this, and plus R is same for both, right? You see, plus R is same for both the molecule, but here we have additional minus I also. That's why the acidity of this is more than that of para position methoxyphenol. Okay, so there are like this kind of some questions you can get. So where you have to where you have to think on plus I or minus I, okay, plus R, minus R, all these things you have to understand. You must have to keep in mind. Okay, so one more very important comparison we have. Okay, and that we'll see. One more very important comparison we have, and that is, just a second. Okay, so one more very important comparison I'll tell you just now. If we have OH and NO2, both are present in the ring. Okay, OH and NO2 both are present, like you see, and these type of questions they have asked in JE. So just change the color. Suppose you have OH here, and at this position, ortho position, we have CS3 present, and here we have NO2. Okay, and now in the second compound, suppose if I change the position of CH3. Okay, if CS3 here, here, here we have NO2, and here we have OH. Okay, now in these two, which one is more acidic? Okay. Now you see, if I consider the first um, like compound into this, you have, what is the difference, like how do you approach this question? That first of all you have to understand. We know when any group present at ortho position, so there may be some SIR, okay, static hindrance, static inhibition of hindrance of resonance. Okay, so if I write down here, in both the molecule SIR possible, SIR here and SIR here. Both the case it is possible. What is SIR? Steric, it is steric inhibition of resonance. Okay, means because of steric hindrance, resonance inhibited. Okay, inhibition of resonance. Okay, you all must have done this thing in GOC. Okay, but since we are doing this in detail, so I'm discussing all this again and again. Okay, so what happens here? We have OH and CS3. So in these two we have repulsion, in these two we have repulsion. Okay, so where the repulsion is more, right, then it is difficult to remove H plus, right? Where the repulsion is more, it is difficult to remove H plus from there. Okay, because of the resonance is inhibited in this case. Okay, so what happens in this, you see, it depends in the size, since the position of CS3 is different in the two molecule, so it depends on the size of NO2 and the size of OH. Which one will have more size, will have more uh, steric crowding over there, more repulsion, more hindrance will be there. Okay, so what happened in this second compound, more SIR is present over here. Suppose this one is first compound and this one is second compound. So in second compound there is more steric inhibition of resonance. Okay, because of the large size of NO2. NO2 is in larger in size than OH. This information I am giving you have to keep this in mind. Okay, since 2 has more steric inhibition of resonance, hence the removal of H plus is difficult over here, because when you remove H plus, this negative charge must get stabilized through resonance. Okay, suppose if I put negative charge here to make you understand, when you remove H plus, we'll have negative charge here and we'll have negative charge here, right? So when this negative charge is resonance stabilized, then the removal of H plus will be fine, because the anion is getting stable through resonance, right? And resonance depends on this steric crowding. If this steric crowding is more, then resonance is difficult, and hence the stability of anion will be less, and that's why the acidity will get affected. So since OH has lesser size than NO2, so here we have more steric inhibition of resonance than this, and then the stability of negative charge of this is less over here, and hence the stability or the acidic order is this, stability order will be this also. Okay, so this compound is more acidic than this because of SIR. Okay, so here we have more SIR because of large size of NO2. Here we have less SIR because of small size of NO2. Okay, now these two, you see, these two are not linear group. Okay, OH is not linear and this is also not linear, because the oxygen here it is sp3 hybridized, and this lone pair is also what, and this nitrogen is also not obviously linear. Okay, it is not linear compound. Okay, but what happens if you have any linear compound present over here? Just we'll see the last example in this. Okay, all these examples are very important question they have asked on this. Okay, so that's why we are doing this uh, here. Okay, so one last example in this we'll discuss. If any linear compound is present, so everything is same, we have OH here, and instead of NO2, here suppose if I write CN, okay, and here also we have CN, and here we have OH. Two CS3 group attached over here. Oh, sorry. one CS3 we have here, one CS3 we have here. See all these specific example we are doing, so you have to memorize this. Okay, what logic we are doing in this, because all these order are given on the basis of Ka and pKa value. Okay, you must remember this, Ka and pKa value, which can be determined experimentally. Okay, by looking at the molecule, we cannot say what is the Ka and pKa value we have. All these are temperature dependent on what temperature we are using and all. Everything plays a role over here. Okay, so Ka and pKa value are experimentally determined value, and whatever acidic order that I am giving you, when we have more than one kind of effect possible, okay, like I effect, R effect are possible, then those kind of questions in which more than one effects are there, then those questions are based on experimental fact. Okay, and that is nothing but Ka and pKa value. So according to Ka and pKa value, we say the compound is more acidic or weak. Okay, less acidic or more acidic. Okay, so if the compound has more Ka value, it is more acidic. Less Ka value, it is more acidic. Okay. So first of all, we calculate this Ka and pKa value. Then we'll see the order, and then we try to explain that in a best possible way. That is what we are doing in chemistry, whether it is inorganic or organic, most of the time. Okay. So here, what happens, since this Cn, the cyanide group is linear. Okay. This is also linear. Okay, so here you see, because of linear nature of this cyanide group, the SIR is very less over here, or no SIR, we can say no SIR, or if it is there also, it is very less, we can neglect that. Okay, but here what happens, this OH is not linear, so here we have more SIR present. Okay, more SIR is there, so hence again the negative charge on this oxygen atom is not getting stabilized through resonance. Okay, so here we do not have resonance, here we have resonance. Okay, because of the by nature of this. Okay, but since these groups are linear, we have, so we don't consider resonance here, but we consider the I effect of CS3, because one compound will have resonance and here we don't have resonance. Okay, so this kind of compound, when we have linear group present over here, will not consider SIR. Okay, will not consider resonance here, but will consider what, the I effect of this group which is present here. Okay, and what kind of I effect it has? All these have plus I, sorry, the arrow should be this, all these have plus I, and plus I effect will be more if it is closer to the functional group, right? So obviously plus I effect will decrease the acidity of phenol, so this compound is obviously more acidic than the second one because of the plus I nature of phenol. Okay, so these two things you keep in mind when we are using SIR and when we are not using SIR. Okay, because of the uh, geometry of the compound, whether it is linear or non-linear. Okay, so all these examples that we have done, you must keep in mind. Okay, how we are doing this. Okay, now you see we have done the various, like the basic chemical sorry, acidic nature. We have done 4 5 6 question onto this. Now we are going to discuss the various, like the preparation method of phenol. Okay, so next we'll see the preparation method of phenol. Okay, so you see, method of preparation. The first compound, the first method, like we are going to discuss here, is from aryl sulfonic acid. Okay, aryl sulfonic acid. So aryl sulfonic acid, the first one you write down, from aryl sulfonic acid. Okay, so aryl sulfonic acid, we have a ring, benzene ring, and on this benzene ring we have what, SO3H is present. SO3H is present. Okay, now in this what happens, if you, if this compound reacts with NaOH, basic medium, okay, then what happens, this H and H2O, OH, H2O comes out into this, and we'll get sodium salt of this compound. That is what it is, ring SO3Na. Okay, and now when you put again NaOH into it, 2 moles of NaOH, fusion takes place and Na2SO3 comes out, and we'll get sodium phenoxide, ONA, plus Na2SO3 comes out. Okay, now finally the sodium phenoxide, you put HCl into it, NaCl comes out, and we get phenol. OH plus NaCl. Okay, so in this what happens, sodium salt of aryl sulfonic acid, it is aryl sulfonic acid. First we'll get sodium salt of this. Okay, sodium salt of aryl sulfonic acid is this, on fusion with NaOH, this is the fusion process. On fusion with NaOH forms C2 C6H5ONA, okay, sodium phenoxide, okay, which on acidification with HCl gives phenol. Okay, this is the first method of preparation we have. Second method we can use from diazonium salt. From diazonium salt. From diazonium salt. In this what happens, benzene diazonium chloride or bisulfate on heating with H2O gives phenol. So what we use, we can use benzene diazonium chloride, zonium chloride, or bisulfate, on heating with H2O gives phenol. This process is steam distillation, which is not in our syllabus. Distillation we don't have to study. Okay, this process is steam distillation. So benzene diazonium bisulfate or chloride, you can write down like this, N2 plus Cl minus we can write. So N2 plus and HSO4 minus. It is benzene diazonium sulfate plus H2O. So when you heat this, what happens? First of all, H2O forms, H plus HSO4 minus H2O forms. Okay, N2 also forms. Okay, and OH attached onto this benzene ring. Okay, any reaction of benzene diazonium chloride, that also we have discussed in amines chapter. Okay, any reaction of benzene diazonium chloride evolves nitrogen. Okay, generally most of the reaction. So OH from H2O comes over here, H plus from this takes this HSO4 minus, forms H2SO4, and we get N2 into this nitrogen. So this is the reaction of benzene diazonium chloride or sulfate if you have. Okay, if you take benzene diazonium chloride, okay, so we'll get HCl, not H2SO4. Okay, we'll get HCl, not H2SO4. Okay, now the next method of preparation we have, that is third one, that is phenolic phenolic acid with soda lime, NaOH. Phenolic acid with soda lime. Okay, so phenolic acid with soda lime, decarboxylation takes place. Okay, so in this what happens? Decarboxylation takes place. To give phenol. To give phenol. So phenolic acid is this. We have OH and COH, both are present. And this, when you heat with NaOH with CaO, then it forms sodium salt of phenoxide ion, which when you put into H plus H2O forms OH plus NaOH. Okay, Na2CO3 also comes out into this. Okay, CaCO3 also comes out into this. Okay, this reaction, but we'll get this. NaOH CaO gives ONA, and then H plus. Whenever you have phenoxide compound like this, you put acidic hydrolysis. If you do, you will get phenol into this. Okay, so this is again one of the method we have into this. Okay, now the last one we are going to discuss into this, that is cumene phenol process. Okay, the last one I'll just rub it off. Okay, cumene phenol process. Fourth one. In this reaction, cumene is oxidized. Okay, in this reaction, I write down just 1-2 line into it. In this process, cumene is oxidized in O2 in alkaline medium to cumene hydroperoxide, which is then decomposed. In short, I'll write down, which decomposed by H2SO4 into phenol. Okay, now you see cumene is what? Cumene is this. We have a ring phenyl group, then we have CH3. Okay, now with atmospheric oxygen, we have this OH minus. So when this is heated with this, pH CH3, just wait one thing. CH3 H3, and we get here OOH, peroxy linkage. Okay, this is a like free radical mechanism it follows. Okay, this particular compound is cumene, and this one is cumene hydroperoxide. Cumene hydroperoxide. Okay, this in acidic medium, when it reacts with H plus, so this H plus comes over here and H2O comes out. This H plus comes over here, we'll get OH, H positive charge with it, and finally this H2O comes out. Okay, so what happens, you see, I'll just write down the just a little bit of explanation we'll do into this. So we have this pH C CH3 CH3 O OH, and this lone pair over here, if it takes this H plus from the acid, so we'll get H over here and positive sign on this. Finally, you see there's a rearrangement which takes place into this. And when you heat this phenyl group, it comes with this bond pair, okay, and attacks onto this oxygen atom, because this oxygen will have positive charge when this H2O comes out, since this oxygen is taking this bond pair of electron to it. So H2O goes out, this positive charge is highly unstable. This phenyl will get rearranged onto this. This takes place on its own. And we get what? We get pH O CCH3 and CH3. Okay, now from this it is like easy to understand it. You see here, which decomposed by H2SO4. This H2SO4 also gives what? H plus. This H plus ion get attached with this oxygen. Again, the lone pair attacks onto this H plus, and we get this pH OH CCH3 and CH3 here. And since it donates its lone pair to this hydrogen, so here we have positive sign on it. Okay. Now in this we have PHOH, right? And CH3 whole twice, CH we have, right? Okay, fine. So what happens finally, you see, this bond pair is taken up by this oxygen, and we'll get what? This bond pair comes over here. We'll get PH OH, which is phenol. Okay, we'll get PH OH, which is phenol. One thing I have missed here, oh sorry, this you see, when this bond pair is taken up by this oxygen, so you must have positive charge here that I missed. Okay, we must have positive charge onto this. So here what happens, I'll just write down this again. So you see this positive charge, and we have first here H2O, right? So from this H2O, H plus comes out, minus H plus, and OH attached onto this positive charge carbon atom that you have. Okay, so this minus of H plus will have here, right? H plus comes out, and this OH minus of H plus, and this OH minus from here it comes onto this carbon atom. So we'll get this PHO C CH3 CH3 and OH here. Okay, now we have acid H plus. Okay, so this H plus comes over here, and we get this PHO C CH3 CH3 OH here, and here we have H with positive charge onto this oxygen atom. Okay, now next thing is what this positive charge is taken up by this oxygen here, so we'll get PHOH, which is nothing but phenol we have, and we'll get CH3 COH CH3 with positive charge onto this carbon atom. Okay, so better I write this. Okay, so the last step in this, we have got phenol over here, and now to complete this reaction we have OH present like this. Finally, this is the electron deficient, so it takes this bond pair of electron, and from this molecule H plus comes out, and we'll get CH3 C double bond O CH3. So we'll get into this acetone plus phenol. This we also call it as cumene hydroperoxide and peroxide rearrangement, and this is also known as cumene phenol process. So basically the conversion of cumene into phenol, it is there, phenol and acetone. Okay, okay, so this is it. Like for today we have finished the preparation method of phenol. Okay, next class will start with the chemical reactions, the properties and various chemical reaction properties. We have already, the important one we have done, that is acidic nature of phenol. Okay, so the next class will see various chemical reactions of phenols, and probably will finish ethers also in the next class. Okay, so that is it for the alcohol chapter, alcohol, phenol and ether. So yeah, so by next class we'll finish this. Okay, so thanks everyone to join this session. Okay, so this session will be available in the recording version of this will be there on the Centum website. Okay, on our channel. Anytime if you want, you can go on to the channel and you can see. Okay, so yeah, thanks all, thanks for joining. We'll see next class. Thank you.